Okay, so we are going to talk about acid-base titrations. So titrations are a general experimental technique that can be expanded on into other types of chemistry. But we're only going to talk about it with acid-base reactions this week because we're talking about acids-bases. So this is a really key experimental technique. And so this is a what we call a wet chemistry technique because it works with water-based solutions, aqueous solutions, so we call it. It's not computational. It's not a really specific piece of electronic equipment. It's really just putting together aqueous solutions and looking for some sort of indicator color change. That's really what it boils down to. And so we call it a wet chemistry technique for that reason. And what we can do with this technique is we can use it to measure molarity of acid-base solutions. If we don't know the molarity or we don't know it very well, we can use this to get a very specific value on that molarity of the concentration. Or we can use it to find the molar mass of an acid. That we don't already know the molar mass to. So, let's talk about the setup, and then we'll get into how we do the calculations with the data. Alright, so our setup is that there's going to be a burette, which is it's kind of shaped like this marker actually. There's going to be a fine end to it, fine tipped end, and there's an opening, and so there's a little knob we can turn here, and we can open this and we can dispense liquid, and it's measured. So we can go like, okay, we've added 10 milliliters, 20 milliliters, 30 milliliters, 40 milliliters, 50 milliliters. It's graduated. We can read it, usually down to the hundredth of a milliliter. And we can very precisely add drops or half drops, so we can move just a little bit of liquid as needed out of this. And as long as we know the concentration of the substance in here, we'll be able to figure out the concentration of our sample down below that we're pouring this into. And we'll talk about that more in a little bit. So first off, we know the concentration inside our burette. And so, if we want to know the concentration of an acid, we put a base in the burette and we know what it is. If we want to know the concentration of a base, we put an acid in the burette and we know what the concentration of it is. So we have to know it to be able to determine specifically what the concentration is of the substance we're reacting it with. So, in our burette, it will be containing a solution of known concentration, and this is known as the titrant. So we titrate with the titrant, and it is used to add measured amounts, volumes, of our known solution and we keep adding it until the sample is neutralized. And this is known as the end point, or the equivalence point. And how do we know we got there, right? You can't just look at something and know you've neutralized it. Well, you can use a pH probe, or you can use a pH changing color indicator. And so you look for, depending on what indicator you work with, there's a whole section of your book on them, you look for a specific change in color. So for example, if you use phenolphthalein, which is a pretty common one when you're adding base to acid, you look for it to go from clear to faint as faint of a pink as you can get it to stay. So if you go too far, it becomes too bright of a pink. And there's no taking the acid out. So if you overshoot, you're kind of stuck. You just got to start over. So you want it to just turn just the faintest pink, and you go, I reached the equivalence point. All right. That's how you know, is by a color change. So, or you just measure pH with a pH probe. But often this is going to be indicated by color change from an added indicator solution. Again, creative with names as always. It's indicated by an indicator solution. And you'll get to play around with this stuff in the simulation, which is too bad because it's one of my favorite labs to do. And like I said, that phenolphthalein indicator that goes from colorless to faint pink. If you overshoot, I call it a violent shade of pink. One of my favorite stories to tell about that, one of the labs that I taught that did this, because basically every school I've ever taught at has done this experiment with phenolphthalein, is one time I had a student show up to lab, and she wore like the most bright, vibrant pink coat. It was unreal. And she didn't take her jacket off in lab either. She kept it on. I don't know, I guess it was cold in there or something. It was winter. It was winter quarter, so and it was on the north side of the building, so maybe it was a little chilly. But oh man, the group, so the lab was situated so that like two students would work together on one side of the table, two students would work together on the other side of the table. And so she's over here in a pink lab coat, and then these two guys are over here trying to figure out if their solution is pink or if it's picking up the color from her coat and from like refraction. And so that was a good day. I've never been that's as proud as I could be of one of my students. You know, she really screwed up the people across from her, and in the just the perfect way. I mean, the coat was like exactly the right shade of pink. It was perfect. It was unreal. And then she kept it on the whole time. Like she was not. It was pretty good. So let's see here. And so you can use different indicators depending on what you're working with. It's usually easier to see the difference between there being color or no color, but sometimes you have to use an indicator where you have to be like, is it yellow? Is it pink? Is it blue? Is it yellow, green, or blue? I guess that'd be the more normal transition of an indicator. And so it can get a little bit messy, like is this blue or green, blue or green, blue or green? So generally it's easier to go, is it pink or not pink? I've still been asked by way too many students, you know, they hold up as they mix their solution. They go, is this pink? Is this a pink solution? And I go, I don't know, you tell me, because I'm so helpful. I'm like, does it look pink to you? And then I'll be nice and I'll show them a trick, like you can put like a white sheet of paper behind it, and that helps. But I don't tell them if they have the pink color or not. I leave that up to them to decide. I mean, you know, can't do everything. It's college now, right? You should be able to tell if something's pink. And then I would make an exception if I had two lab partners that were colorblind. I've never had that happen. Sometimes there's one, and it's great because they'll still argue about if it's pink or not. I don't know how that works. It's fascinating. So, or sometimes just like, I don't know, you tell me, is it pink? Is it pink? Okay, good, let's write the number down. But I have had it happen where like I've had a colorblind student arguing with their lab partner about the color of their titration. So, the world we live in. Alright, so let's do an example. Okay, and so we've got a burette. So I'm going to draw very crudely. So it's got graduated marks for volume. And, you know, there's generally like an endpoint here that's like, you know, 50.00 milliliters. So it always screws students up because it's backwards. Alright? So there's also usually like a handle here that you can use to turn. And so it goes from 0 to 50 as you go down. And so there's like some level of volume in there at the end. Well, actually, it's not that wavy. It's, you know, nice shaped meniscus. And underneath, we have a beaker with our sample. And so let's say we measure out our sample to be 25.00 milliliters. And it's an unknown concentration of HCl. So we have an HCl solution. We don't know the molarity. We're going to figure it out. We do know in our burette we have 0.1000 molar sodium hydroxide. That's our titrant. Now sometimes the sample is called a titrand. I don't like to use that term because it's really hard to differentiate, so I'm just always going to call it sample, but be aware if you ever see that language. Titrant, titrand. Alright? The problem is if I get lazy and I just say titrand, they sound too similar. Alright, and then we use, say, a phenolphthalein indicator or something. And so we add, we get a color change after adding 38.50 milliliters of the sodium hydroxide. So this is our equivalence point. We reach it after adding 38.5 milliliters. So this is what we would work with. Like, we have all the data now. And so what we're going to do is we're going to be like, oh, okay, well, let's see. Well, alright, I've got a volume here. You know, how many moles of NaOH did I add? Alright, well, let's see. I need to go 1 liter for every 1,000 milliliters. Okay, that gets me to liters when I divide by 1,000. And then there is, you remember, we know this concentration, so that means there's 0.100 moles of, well, we'll just say OH minus per liter. And then there's going to be 1 mole H plus for every 1 mole OH minus. And so we just punch that up in our calculator. We just solve this. And we get 0.003850 moles of H plus. And HCl is what we call a monoprotic acid. So that means we only have, you know, for every mole of HCl, there would be 1 mole of this stuff. So that means that it's 0.003850 moles of HCl. Okay, and so now I need my molarity. Well, I've got moles, so there was this many moles, this many moles in this volume. Alright, and so I want to make sure it's moles over liters though, so I go 0.003850 moles HCl over, let's see, it's 25.00 milliliters, but that's 1 liter for every 1,000 milliliters. Okay, and I just carry through on that calculation and I get 0.1540 molar HCl. Okay, that was a very sloppy way of doing this, but I was just kind of feeling my way through with the numbers, but we can streamline this. We can explain this a little bit more clearly. So, here's what we need. We need the molarity of HCl. Okay? Here's what we know. The milliliters of NaOH. Well, we can get this to moles of NaOH. And you should be thinking to get to moles because we have different compounds on the end here. Okay? And so then we can get this to moles of HCl. And we can get that to molarity of HCl. Okay, and so this is going to use the molarity over here. This is going to use stoichiometry. And this is going to be dividing by volume of our sample. And so you do have to be a little bit careful because you get two volumes. By the way, there's one molarity and two volumes. So part of your brain is going to be like, I got to do the dilution equation. No, don't do the dilution equation. It's not going to work for you. It's not going to work. It's not a dilution problem. At no point in here do you see the word diluted or dilution or dilute, so don't do it, okay? Don't do it. So, that's what we did. It was a little bit messy, but we're going to go from a volume to a molarity. And that's kind of the general approach. And so we can write that out a little bit cleaner, a little bit like we've seen it, more like we've seen it before, and we'll do that in the next problem. And another detail I'll point out, you don't generally just do one trial and be like, okay, I know what it is. You know, in lab you're going to do like 3, 4, professionals are going to do like 100. Like, you really want to make sure you know what something is. You don't mess around. So, what we just did is known as a standardization. We standardized the HCl solution because this means that we determine concentration of an acid or base solution to 3+ significant figures. And we determined ours to 4. 1, 2, 3, 4. So we standardized this HCl. This is a pretty common trick, and usually what you actually have to do is you have to standardize your NaOH and your burette, because when you make that stuff, you put it on the balance and say you use 50 grams of sodium chloride to make your solution. The problem is you don't have 50 grams of sodium chloride on the balance because it's what's called hygroscopic. It pulls moisture from the air, and so if you sit there and you watch the balance, you'll see the mass is slowly ticking up, even though you're not adding anything, because it is pulling moisture from the air and water is getting added onto that balance. And so it's impossible to know exactly what the concentration of NaOH is. So, sometimes you can just use a balance and make a standardized solution, and that's great, but you can't do it with NaOH. So, let's do an example here, where we have to figure that out. So let's do another example of a standardization. So we don't know the concentration of the sodium hydroxide in our burette. It's a common thing we have to do. We have to figure this out. If you were doing this lab in person, you would be doing this. You would prepare a sodium hydroxide solution, and then you would have to standardize it, and then you could titrate an unknown with it. So it's a multi-step problem. Because of the fact that sodium hydroxide cannot be reliably massed on a balance, due to the fact that water starts mixing in with it spontaneously from the air around it. So, we got to figure that out. So what we do, we prepare a sample. So if you don't know what's in the burette, you got to know what's in the sample. So we're going to prepare a sample and we're going to know exactly what's in it. And it's going to have 0.2050 grams, using every digit that balance gives us, of potassium, hydrogen, phthalate, PHTH. Always a weird way to start a word. And so this is KHC8H4O4. And we can also say that it's what we call monoprotic acid, so it reacts 1-to-1 with NaOH. So that's for our stoichiometry. So we get 1 mole of NaOH for every mole of potassium hydrogen phthalate that's in our sample to reach the equivalence point. And our molecular weight is 204.22 grams per mole. And so this is dissolved in the water. Doesn't really matter how much. With a couple drops of, man, I can't spell, phenolphthalein. Alright, you know what? I need to go to the next line. That's a long word. That's always good when the problem takes up the entire paper. Why not? Or actually, we'll just say, we'll be general. We'll just say of indicator solution. Okay. And so 23.24 milliliters of NaOH gets us to the equivalence point. So we dispense 23.24 milliliters out of our burette. Oh, this is such a sloppy problem. Sorry. I had to scribble a lot of stuff out. Just looking at too many things at the same time. Okay, so however many moles of KHP were in our sample, that's how many moles of NaOH are in 23.24 milliliters of our NaOH. And that's what we're trying to standardize. Okay? So, here's our overall roadmap. We know our grams of acid, and we need to get to molarity of NaOH. Well, I've got different substances, so I'm going to have moles in the middle. Luckily, I think we're all pretty good now at going from grams to moles, right? This is the good old-fashioned way. You gotta love a solid that you can put on a balance, and that's what we have here. So it's our moles of acid, our potassium hydrogen phthalate. And then we can get this to moles of NaOH. And then we can go to molarity by dividing by volume here. Okay. Can we go here to here? Yeah, this is a 1-to-1. We talked about that. And can we go from here to here? Well, yeah, we use the molecular weight. Okay. So we have all the pieces for this. So how many grams of acid did I work with? Well, I had 0.2050. And I'm going to abbreviate it KHP, potassium hydrogen phthalate. So that's not a phosphorus. And my molecular weight was 204.22, so I have 1 mole KHP for every 204.22 grams. Okay. And it's a 1-to-1 reaction. Alright, so I have 1 mole NaOH for every 1 mole of KHP. Okay, and I'm going to solve it here to get my moles of NaOH, and then I'm going to divide by the volume to get my molarity. So, I had 0.001, if I just solve this out, 0.003 and an 8 I don't really get to keep, moles of NaOH. If I divide that by my volume of NaOH that I used, which was 23.24 milliliters, and then convert that to liters, I get 0.04319 molar NaOH. So we have standardized, our sodium hydroxide. I apologize, I didn't realize that went out of view. So I took my moles, I divided by my volume in liters, so I did a conversion here, so my milliliters go away, and that gets me moles per liter. There we go. Alright, so we are almost home free here, and lots of opportunity to practice this on the practice worksheet as well. But there is one more type of problem we can solve with our titration. And that is if we have an acid or a base and we don't know the molar mass of it, we can determine it experimentally with a titration. So I'm just going to be sticking to an acid here, but just keep in mind you could flip. You could put an acid in the burette and titrate a base in your sample and do the same thing. So you need two things to find the molar mass of something. You got to know the mass of your sample, and you got to know how many moles were in your sample. The mass is easy. You just weigh it. You just throw it on a balance, and then you dissolve it in water. That's your mass. Moles, you get that from the titration, and then you just go grams over moles, molar mass. So it's a little bit different than what we've done before, because we're not adding stuff up from a periodic table. We are experimentally determining this, because we don't know the formula, because it's unknown. If we don't know the formula, then we got to measure. Can't solve it with arithmetic. We're going to solve it with titration. So here's kind of the general overview. Our sample is prepared with measured mass of unknown acid. Boom. We got mass. Looking good. That's half of what we need for a molar mass. And then what we do is titrate sample with standardized NaOH. That gets us moles. Boom. And then our molar mass is going to be mass over moles. Boom. We got a final answer. That's all there is to it. 3 easy steps, right? How hard could it be? Alright, well, let's get to work on one here. Let's do an example. And then we are done for the week. Well, I'm done. We're done filming. Or watching video. There's plenty of homework to do and stuff. Practice worksheets. Make sure this is making sense. Alright, so if 42.50 milliliters of 0.1009 molar NaOH are needed to neutralize a 0.4931 gram sample of an unknown acid. What is the molar mass of the acid? Alright, so here is the chemical equation for this as well. So we know the chemical equation, so this is just part of what we know. Alright. So H2A, we don't know the formula, so A is a stand-in. We know it's going to release 2 H pluses, so it's a diprotic acid. So it's going to react with 2 NaOHs. And we are going to get 2 waters and a salt, which is Na2A, which is aqueous. So this is a diprotic acid. It releases 2 H pluses. It's a 2-to-1 reaction. So there's monoprotic, releases 1 H plus, diprotic releases 2 H pluses, and triprotic releases 3 H pluses. We won't worry about anything beyond that. Alright, so I got enough room here. We'll do the plan. I'll pull out another sheet. We'll do the math. So I've got to go from volume of NaOH, and I've got to get all the way over to my molar mass of my unknown acid, H2A. So again, A is just a stand-in for the acid anion. Alright. So what do? Well, I've got 2 different compounds, so I got to get to moles in the middle and then convert over to what I need on the right. So I can go straight from volume to moles using the molarity. And then I can go to moles of H2A using the 2-to-1 stoichiometry. And I can go over here by going grams over moles. Alright, so that's our plan. So what I'll probably do is I'll solve for the moles, and then I'll pull the grams from the question, and kind of, I usually break it up a little bit. You'll see. So, let's get tricky with this here. Maybe I can keep a lot of this stuff on the screen at the same time. That's right, master of origami. Okay. Now I have one big sheet of paper. Look at that, I just keep scrolling and scrolling. Alright, so my volume of NaOH was 42.50 milliliters. Okay, well if I'm going to use molarity to convert that into moles, I need to convert milliliters to liters. So there's 1 liter for every 1,000 milliliters. That cancels the milliliters. I'm going to use molarity. What is my molarity? 0.1009. Oh, there it is. That's moles per liter. That's perfect. So I have 0.1009 moles of NaOH per liter. That cancels liters. And then I use my stoichiometry and I go, well, there's 1 mole of this for every 2 moles of that. Alright, so 1 mole of H2A for every 2 moles of NaOH. Okay. And then I just solve to my heart's content. And I get 0.002114. I'm going to keep an extra working number around, an extra 1 moles of H2A. Alright, and so my molar mass, I've got grams, I've got moles. I'm not done. It feels like maybe I did so much work I should be done, but my molar mass has not been determined yet. So in my sample, I had this many moles. And remember, molar mass has units of grams per mole, so that's going to have to go underneath. Okay, but how many grams were in my sample? Well, let's see here. Oh, I had 0.4931 grams on the balance at the start of this. Alright, so 0.4931 grams. And then I just do the math. I just go this divided by that, I get 4 sig figs at the end, and it ends up being 233.2 grams per mole. Not too shabby, huh? All right, so that'll do it for this week. Hopefully this helps you out with the lab. There's practice sheets too. Maybe it'll make more sense without me talking about it. Who knows? Just seeing the numbers get laid out sometimes makes things clearer. And if you do have any questions, just let me know. I will be predisposed this Thursday because of Thanksgiving. And if I just happen to be reusing these lecture videos in the spring semester, which I'm going to be, let's be honest, I'm just going to tell you right now, all of you in my spring class, it is mandatory. You must celebrate Thanksgiving this week. That is part of your homework. All right? No exceptions. And I'll know if you didn't. Don't ask how, but I'll figure it out one way or another. I'll be like, you don't look like you ate any Thanksgiving fixins. You don't get full points on your quiz. Yeah. Because a lot of us aren't going to be able to celebrate Thanksgiving quite the way we want this year. So whatever. So yeah, if it's springtime, enjoy the light week. Whatever. If it's fall, happy Thanksgiving. Celebrate safely, and hopefully you can do something. If nothing else, you can video chat with family and awkwardly try to talk at the same time, right? Just like a work meeting or something. But if you do have any questions about the stuff, let me know. I'll be checking my email and stuff again by Saturday, I'm sure. So if you are working on Thursday and you don't know what to do, take a break. Just take a break. Enjoy the long weekend. Or, hopefully you're not having to work. I've worked grocery, so I've had to work on Thanksgiving Day. And that's definitely better, I think, than when I was working retail and had to work Black Friday. I know which one I prefer. I always thought it'd be terrible working at a grocery store on Thanksgiving. But it's only like a half day, so that's a lot better than having to go and huck TVs at a Sears at 4 in the morning. That's a much bigger cramp on your Thanksgiving, in my opinion. But anyway, if you have to do that too, that's great. Go make some commission or whatever. Go get them. I certainly didn't on my Thanksgiving. Who buys a TV at 4 in the morning? The answer was a lot of people from the other guy I worked with. He had them lined up. I couldn't get anybody. All right, so yeah, if you do have questions, let me know. I'm happy to help. Otherwise, good luck, and we will pick up a lot of this material. So there's kind of some stuff I did early, and then I just pulled titrations to this week because of the lab. So a lot of that stuff we talked about earlier, if you didn't feel like it was really a complete conversation, I agree. It's not. We're going to talk about it more next week. So just hang in there, be patient, and hopefully it'll all come together next week if it's not clicking right now.